In this short video, we're going to define a couple of terms. At least one of them you will have seen before. And then we're going to show that the operator known as the modulo operator is an equivalence relation. So let's start. For all of these numbers, a, b, n, x, and y, integers, with this one in not a zero, we say that a divides b, and the way we write it is a vertical line b. Some people say a goes into b evenly. If there's some integer k where you can take a times k and get b. So a goes into it evenly. Okay, the second one is, suppose x and y are related. So let me rephrase that. Suppose x and y are related if and only if n divides x minus y for some fixed value of n. So what that says is that n divides x minus y, so there's some number k I could multiply n by to get this value. This relation on Z is called congruence modulo n and is denoted as this. This says x is congruent to y modulo n. We'll do some examples that will explain that better if you haven't seen this before. Okay, show that the integers, comma, congruence modulo n is an equivalence relation. So, what does that mean we have to do? We have to show that it's reflexive, symmetric, and transitive. I've already started this. Reflexive. N divides 0. We know that because n times 0 equals 0. Every integer divides 0. 0 doesn't define anything. You'll never see 0 on the left-hand side of this divide operation. N divides 0. In other words, n divides x minus x, because x minus x is 0. That implies, by definition of modulo, x is equivalent to x modulo n. Since x and x are equivalent, that means that it is reflexive. Okay, the next one, symmetry. X is equivalent to y in modulo n, implies that n divides x minus y. Well, what does that mean? That means n times k, I'll call it k1, is equal to x minus y for some integer k1. That's just the definition. Well, let's see what that means. That means that n times negative k1 would be equal to y minus x. Right? Because if you multiply both sides by negative 1, I did it here by multiplying k1 times negative 1. If you multiply this by negative 1, you get negative x plus y, which is y minus x. So that tells us that n divides y minus x. And that's what we needed to show. X is congruent to y. All what we have to show now is y is congruent to x. And by definition, if this is true, y is congruent to x in mod n. And in the transitive case, here we have to say if x and y are equivalent in mod n and y and z are equivalent in mod n, then x and z are equivalent mod n. So we'll start that off by if x is equivalent to y mod n, and y is equivalent to z mod n. I'm having to go down a little bit here. Then that means that by definition, n divides x minus y, and n divides y minus z. Well, that implies that n times k1, and I just realized I didn't need to call that k1 in the previous one since I only used one value of k. In this one, I'm going to need a k1 and a k2. That implies n times k1 is equal to x minus y, and n times k2 is equal to y minus z. That's just the definition of what it means for n to divide something. And what do we want to show? Thus, I want x minus z. X minus z I could rewrite as saying x minus y plus y minus z. Just using some simple arithmetic. And what is that equal to, though? X minus y is in k1, and y minus z is in k2, which is n times k1 minus plus k2. So x minus z is equal to n times an integer. That means n divides x minus z, and x is congruent to z mod n.